Welcome to G Fun Facts Online. We often think of the Earth's great ice sheets as static, silent giants. But what if I told you that beneath that frozen veneer lies a fiery world, and as our planet warms and the ice melts, we might be waking up the giants underneath? This isn't science fiction. This is the story of a profound and often overlooked connection between ice and fire, a phenomenon known as post-glacial volcanism, where melting glaciers can trigger more frequent and more explosive volcanic eruptions. The great ice sheets, some several kilometers thick, are unimaginably heavy. This immense weight presses down on the Earth's crust and the underlying mantle, acting like a giant cap on the volcanic systems below. It suppresses the molten rock, or magma, keeping it and its dissolved gases locked deep within the Earth. But as global temperatures rise and this ice melts, the pressure is released. The crust, freed from its colossal burden, begins to slowly bounce back in a process called isostatic rebound. This unloading of the crust doesn't just happen quietly. It has dramatic and fiery consequences for the volcanoes that lie beneath. The first clues to this incredible connection emerged in the 1970s, with scientists looking at a place famous for both ice and fire, Iceland. They discovered something astonishing. As the last great ice age ended, between about 10,000 and 15,000 years ago, the rate of volcanic eruptions in Iceland skyrocketed. It wasn't a small increase. Eruption rates surged to levels 30 to 50 times higher than they are today. It became clear this wasn't a coincidence, but a direct geological response to a changing climate. So how exactly does melting ice light a fire under a volcano? The mechanism is a fascinating chain reaction rooted in basic physics. First, there's a process called decompression melting. Think of it this way. Pressure affects the melting point of rock. Under the immense weight of a glacier, rock in the Earth's upper mantle can remain solid, even at very high temperatures. But when you remove that weight by melting the ice, the pressure drops. This drop in pressure lowers the rock's melting point. Suddenly, rock that was stable can begin to melt, generating vast new quantities of magma. It's like the planet itself is turning up the burner, providing fresh fuel for future eruptions. But it's not just about creating new magma. The unloading process also affects the magma that already exists in chambers deep beneath the surface. This magma contains large amounts of dissolved gases, like water vapor and carbon dioxide, held in solution by the immense pressure. Here, the perfect analogy is a bottle of soda. As long as the cap is on, the carbonation stays dissolved in the liquid. The pressure from the ice sheet is that cap. When the ice melts, it's like twisting the cap off the bottle. With the pressure released, those dissolved gases can finally come out of solution, forming bubbles. These bubbles expand rapidly, dramatically increasing the pressure inside the magma chamber. This internal pressure pushes outwards, seeking a way to escape. It makes eruptions far more likely, and because of the massive amount of expanding gas, it can make them far more explosive. Finally, removing an ice sheet changes the entire stress field in the Earth's crust over a wide area. It can create new faults and fractures, or reactivate old ones. These cracks act as superhighways for magma, providing new, easier pathways for it to travel from the deep chambers all the way to the surface. A powerful example of this entire process can be seen in the Andes at the Mochochocuenco volcano in Chile. During the peak of the last ice age, a thick ice sheet covered this volcano, suppressing its activity. This long period of quiet allowed a massive reservoir of magma to slowly build up deep underground. But when the Patagonian ice sheet began to rapidly melt around 13,000 years ago, the cap came off. The pressure release caused the trapped gases in that deep magma to expand violently, leading to a series of huge, explosive eruptions that carved the volcano into the shape we see today. And this isn't just an Icelandic or Chilean story. Scientists have now found evidence of this post-glacial volcanism all over the world, showing it's a fundamental planetary process. Let's travel to Southeast Alaska. By studying sediment cores from the ocean floor, researchers uncovered a dramatic spike in volcanic ash layers. They traced this ash to the Mount Edgecumbe volcanic field. Between 13,114, 600 years ago, this volcanic field produced 19 separate eruptions. This burst of activity coincided perfectly with the rapid retreat of the Cordilleran ice sheet and the subsequent uplifting of the land. The connection was undeniable. We see a similar pattern all along the Andes in South America. As the vast Patagonian ice sheet retreated, multiple volcanoes roared to life with more frequent and more powerful eruptions. Perhaps the most concerning hotspot today is Antarctica. The West Antarctic ice sheet, a region melting at an alarming rate, sits directly on top of a massive volcanic province with at least 100 known volcanoes. Evidence from the end of the last ice age shows that past glaciation here also triggered an increase in eruptions. The giants under the Antarctic ice have awakened before, and as the ice thins again, they may be stirring once more. The effect can even be felt in places that weren't covered by the largest continental ice sheets. Take the Yellowstone supervolcano. While it was covered by a much smaller local ice cap, studies suggest that when this ice melted, it enhanced the rate of mantle melting beneath the region by as much as 19 times. While this didn't cause a super eruption at the time, it did generate a significant amount of extra magma and released large quantities of carbon dioxide from the mantle, proving that the entire crustal system was profoundly impacted by the changing weight of the ice above. This historical record serves as a critical and urgent warning for our present. With global temperatures rising at an unprecedented rate, the world's remaining great ice sheets in Greenland and Antarctica are melting faster than ever. We are essentially rerunning the experiment of the last glaciation, but this time in fast forward. The concern among scientists is not just that we will see more eruptions in places like Iceland, Alaska, and Antarctica, but that these eruptions could be particularly violent. The long periods of suppression under the ice can allow enormous, gas-rich magma reservoirs to accumulate. When the pressure is finally released, the resulting eruption can be catastrophically explosive. This could create a dangerous planetary feedback loop. While a single massive volcanic eruption can have a temporary cooling effect on the climate, by spewing sunlight-reflecting sulfate aerosols into the stratosphere, a sustained period of increased volcanism would do the opposite, would pump enormous amounts of greenhouse gases, primarily carbon dioxide, into the atmosphere. This would contribute to even more global warming, which would accelerate ice melt, which in turn could trigger even more volcanic activity. Furthermore, when volcanoes erupt beneath an ice sheet, they release immense geothermal heat. This melts the ice from the bottom up, lubricating the base of the ice sheet and accelerating its slide towards the ocean, further contributing to sea level rise. The link between melting ice and restless volcanoes reveals just how complex and interconnected our planet is. It shows that the consequences of climate change aren't limited to the atmosphere and oceans. They reach deep into the Earth's crust, shaking the very foundations of our world. While the changes within magma chambers happen over geological timescales of hundreds or thousands of years, giving us some time to prepare and monitor, the response to glacial melting is, in geological terms, almost instantaneous. The awakening of volcanoes in West Antarctica, the coasts of Alaska, and the fiery heart of Iceland is not some distant, hypothetical threat. It is a present-day reality and a critical area of scientific monitoring. Understanding this fiery consequence of a melting world is essential as we navigate the multifaceted challenges of our future on this rapidly changing planet.